In modern astronomy, every supermassive black hole is supposed to anchor the center of a stellar galaxy. But we are now detecting anomalous giants, completely stripped of their host stars. Optical data from the Hubble Space Telescope reveals quasars burning entirely alone in the void, with the expected galactic halo dropping abruptly to zero. To confirm these objects have actually gone rogue, we have to look for the massive kinetic tracks and environmental wakes of a violent ejection. The initial puzzle behind these anomalous objects began in 2005 with a quasar known as HE 0450-2958. Located roughly 5 billion light-years away, it was observed jointly by Hubble and the ESO Very Large Telescope. When an active black hole reaches millions of solar masses, it should sit firmly embedded inside the dense, glowing core of a galaxy. At a distance of 5 billion light-years away, the surrounding starlight of a host galaxy is usually massive and unmistakable against the dark background. Instead, astronomers found a stark optical separation in the data.
The instruments showed a massive accretion disk radiating immense energy, but the expected stellar signal dropped directly below the detection threshold, leaving the quasar entirely isolated. This absence of stars earned it the nickname the Naked Quasar. It presented a profound observational paradox. If the host galaxy is truly missing, what is feeding the singularity, and how did it end up entirely alone? Astrophysicists immediately proposed a conservative alternative. They suggested the host galaxy was not missing, but simply obscured. A dense cocoon of thick dust, combined with the intense glare from the quasar itself, might be physically masking the surrounding starlight. To test this, follow-up radio and deep infrared observations were deployed to hunt for that hidden stellar population. In some cases, instruments did find evidence of highly disrupted companion galaxies or dust-choked star formation. Yet, even when a hidden galaxy is accounted for, the mass ratio between the stars and the central singularity in these systems remains radically skewed compared to the standard models of galactic evolution.
As deep space surveys from advanced observatories pour in, the data forces us to confront a harsh cosmological reality. A growing number of these supermassive objects are not merely hidden behind dust, they appear to be genuinely hostless. If a supermassive black hole is truly alone in intergalactic space, it did not consume its galaxy. Black holes are not cosmic vacuum cleaners. Their gravity follows strict orbital physics, making it impossible to devour an entire stellar system. This leaves two viable physical mechanisms. The object was born in the dark void as a primordial heavy seed, or it was violently ejected. The latter requires staggering kinetic energy to overcome the binding force of an entire galaxy. While an empty optical image is a compelling clue, the absence of evidence is notoriously tricky in astrophysics. We cannot simply look at a missing galaxy to definitively solve the paradox. We need to catch one in the act of leaving. We must trace the physical tracks, the glowing environmental wakes, and the kinetic data that
To confirm these anomalous giants are actually wandering, astronomers look for the physical signatures of violent motion. We need kinetic data and glowing environmental wakes that empirically prove a supermassive black hole is actively leaving its host. The first compelling evidence of kinetic separation was captured in 2012 by a powerful tandem of instruments. NASA's Chandra X-ray Observatory and the Hubble Space Telescope locked on to CID-42, a distant galaxy located roughly 4 billion light-years from Earth. When researchers overlaid Chandra's thermal heat map onto Hubble's optical imaging, they found two distinct sources of light. The optical center of the galaxy remained anchored, but an intense, localized X-ray source was clearly offset from the core. Tracking this spatial offset revealed that the X-ray point source is physically separating from the galactic center. it is moving outward at a staggering velocity of roughly 3 million miles per hour, completely defying normal galactic rotation. Early alternative models suggested that this migrating X-ray source might simply be an ultraluminous supernova detonating near the galaxy's edge.
But long-term spectroscopic analysis ruled that out. The moving object exhibits sustained X-ray luminosity and the broad emission lines characteristic of a swirling accretion disk. This confirms we are tracking an actively feeding massive black hole in kinetic transit. This shatters the common misconception that a rogue black hole would be a dark, invisible hazard. When violently ejected, the supermassive black hole's immense gravity drags its inner accretion disk along with it. It continues to consume this trapped reservoir of gas, shining brilliantly as an active galactic nucleus, even as it hurtles into the cold, empty void of intergalactic space. This sustained activity leads directly to our second piece of dynamic proof: massive environmental impact. In 2023, deep optical imaging of the dwarf galaxy RCP-28 revealed a monumental linear structure trailing behind it. Hubble uncovered a continuous 200,000 light-year-long streak of newborn stars extending into the dark. Astronomers determined this is the physical wake of a 20 million solar mass runaway black hole.
As this rogue singularity plows through the diffuse circumgalactic gas at 3.5 million miles per hour, it creates a massive supersonic bow shock. The kinetic impact violently compresses the cold hydrogen in its path. That rapid gas compression triggers an intense chain reaction of stellar ignition. The wandering black hole literally leaves a glowing trail of young, hot stars in its wake, creating an environmental footprint twice the width of the Milky Way. Deriving the exact three-dimensional velocity of these runaways does carry some inherent uncertainty. It requires assumptions about their angle of inclination relative to Earth, as we cannot perfectly measure the vector moving directly along our line of sight. But regardless of the exact angle, the fundamental physical reality holds true. Massive, luminous point sources are definitively observed existing and actively migrating well outside of the deep potential wells of galactic centers. These kinetic signatures prove beyond a doubt that supermassive black holes can be forcefully evicted from their hosts. But to understand how something so immensely heavy is moved, we must first look at why they normally stay put.
What kind of catastrophic cosmic force is required to permanently break the gravitational bond? To understand the catastrophic force required to eject a supermassive black hole, we first have to measure the sheer strength of the gravitational cage that normally holds it in place. For decades, standard astrophysics has relied on a tightly bound evolutionary baseline. In this established framework, a mature host galaxy and its central singularity grow as a fully synchronized system. This structural lock is empirically anchored by the M-sigma relation. Across comprehensive statistical galaxy surveys in the local universe, astronomers observe a strict, highly predictable mathematical correlation. By measuring the velocity dispersion, the average kinematic speed of stars swarming within the central galactic bulge, we can accurately calculate the exact mass of the singularity hiding inside. In undisturbed, mature galaxies, the central supermassive black hole consistently scales to roughly 1/10 to 0.5% of the host's total stellar bulge mass. While recent James Webb data shows this coevolution can become highly erratic in the extreme early universe, the M-sigma relation remains an ironclad, proven law for the local cosmos.
Recent 2026 pairwise residual analyses confirm that this stellar velocity dispersion is the single most fundamental property pinning the black hole's mass to the depth of the galaxy's potential well. It is a common misconception that the black hole's gravity holds the host galaxy together. In reality,
Its direct gravitational dominance extends only across the inner few parsecs of the core. It is the broader galactic architecture, constructed from an immense, invisible scaffolding of dark matter, that dictates exactly where the supermassive black hole must permanently reside. That central positioning is not a coincidence. It is continuously enforced by a rigid physical mechanism known as dynamical friction. When an exceptionally massive object moves through lighter stars, its gravity creates a dense trailing wake. This gravitational interaction acts as an inescapable cosmic drag. It continuously bleeds away the moving object's kinetic energy, transferring that momentum outward to the surrounding stellar field.
Even as galaxies undergo hierarchical merging, a violent process of successive collisions, dynamical friction guarantees that the black holes of both parent galaxies will eventually sink inexorably toward the deepest point of the new gravity well. Once settled at the absolute bottom, the black hole's radiation and energetic feedback regulates the galaxy's gas supply, firmly locking them into a shared evolutionary timeline. This proven baseline is precisely why the kinetic wakes and solitary naked quasars tracked by Hubble and James Webb represent such a deep anomaly for modern astronomy. If dynamical friction relentlessly forces these massive objects to the center, they should never be able to leave. Overcoming that immense drag coefficient requires a sudden, devastating event. Escaping the deep potential well requires an immediate injection of pure kinetic energy, an astrophysical mechanism capable of generating more propulsive thrust.
That required thrust does not come from a collision of matter, but from the fabric of space-time itself. To break a supermassive black hole out of its galactic cage, the universe relies on a mechanism called gravitational recoil. The process begins when two galaxies collide. Their central supermassive black holes naturally sink toward the new center of mass, eventually locking into a tight binary orbit. As they spiral inward, their immense gravity churns the surrounding vacuum. According to general relativity, this orbital dance radiates massive amounts of energy in the form of gravitational waves. Crucially, these extreme ripples in spacetime are almost never perfectly uniform. If the two merging black holes have different masses, the waves distort. The same distortion happens if their rotation axes are misaligned. This asymmetry means the gravitational wave emission blasts outward with significantly more intensity in one specific direction. The resulting binary system becomes a highly directional energy emitter. Because linear momentum must be conserved, the newly merged single black hole must violently recoil in the exact opposite direction.
This is not a physical explosion, but a smooth mathematical thrust generated entirely by invisible ripples carrying momentum away. Numerical relativity simulations provide our strongest evidence anchor for this dynamic. By modeling the merger on supercomputers, physicists have calculated exactly how much kinetic energy is transferred to the resulting singularity during that final fraction of a second. The theoretical recoil velocities can be staggering. In extreme configurations, where the two black holes have highly specific, anti-aligned spins, the kick can reach up to 5,000 kilometers per second. That is more than enough to permanently escape any host galaxy. However, there is a strict uncertainty boundary here. Maximum recoil is incredibly rare. Most mergers result in smaller, less dramatic kicks. These weaker recoils simply displace the black hole into a wide, eccentric orbit that takes millions of years to decay back to the center. But when that maximum gravitational slingshot does occur, the black hole is fired out into the void, carrying its immediate accretion disk along with it. It becomes a runaway quasar, burning brightly as it hurtles through intergalactic space.
Gravitational wave recoil is not the only mechanism capable of this. Astronomers also model an alternative, purely Newtonian explanation, known as three-body interactions. This happens when a third galaxy enters the picture before the first two black holes have merged. In this crowded scenario, complex three-body dynamics turn the galactic core into a gravitational pinball machine. The lightest of the three supermassive black holes is inevitably slingshotted forcefully out of the system, leaving the remaining two behind. Both gravitational recoil and three-body ejections elegantly explain the kinetic signatures observed by Chandra and Hubble. They provide a verified physical pathway for a supermassive black hole to be violently separated from the stars that built it. But as our observational tools improve, we are finding anomalies that defy even these extreme kinetic models. The James Webb Space Telescope recently detected a naked black hole in the early universe, pushing astrophysicists toward an even stranger conclusion. What if some of these isolated giants were not violently ejected from an ancient galaxy, but simply never had a galaxy to begin with? To answer that, we have here, deep in the early universe, astronomers are finding isolated supermassive black holes that break the gravitational slingshot theory entirely. These ancient anomalies never violently escaped a host galaxy. Instead, they seem to have been born without one. The most compelling proof of this alternate reality comes directly from the James Webb Space Telescope's Uncover program. By peering through the massive gravitational lens of the Pandora cluster, instruments locked onto an incredibly distant target known as Abell 2744 QSO-1. Observed exactly as it existed just 750 million years after the Big Bang, this target is a 50 million solar mass black hole. But what truly surprised researchers was exactly what the JWST instruments failed to find around it. Deep spectroscopic data revealed a brilliant accretion disk of hot, orbiting hydrogen gas, yet it showed an almost total absence of accompanying starlight. The fully formed host galaxy that should traditionally surround a singularity of this immense size was completely missing. According to standard cosmological models, this observed mass ratio is mathematically incompatible with standard evolution. A singularity weighing 50 million solar masses requires billions of years of steady mergers and stellar feeding, meaning it should be firmly anchored inside a highly developed galactic structure. This glaring observational contradiction introduces the heavy seed, or direct collapse model. Instead of a small black hole slowly growing from the shattered remnants of dead stars, the early universe may have skipped the galaxy-building phase entirely. In that primordial epoch, immense clouds of pristine hydrogen lacked the heavier chemical elements necessary to cool down and fragment into individual suns. Instead, under extreme gravitational pressure, these massive, unbroken gas clouds collapsed directly into themselves. This violent, direct collapse would forge an enormous heavy seed, effectively a supermassive black hole born instantly in the dark void. This mechanism seamlessly explains how a cosmic singularity could achieve such immense scale before a host galaxy could ever assemble. However, this direct collapse model faces intense scientific scrutiny, and alternative interpretations do exist. Some astrophysicists argue this could be a standard stellar mass black hole that underwent highly efficient hyperaccretion, somehow vastly outpacing the growth of its surrounding star cluster. Definitively proving that an early universe black hole is completely naked is also strictly constrained by our instrumental limits. It is exceptionally difficult to empirically verify a total absence of stars at such an extreme cosmological redshift. A faint, diffuse halo of early metal-poor stars could still be hiding just below JWST's current infrared detection thresholds. Finding clear spectroscopic signatures of an old stellar population tightly bound to QSO-1 would immediately disprove the isolated heavy seed hypothesis.
Yet what remains undeniably true is that the baseline timeline of cosmic evolution is broken. Whether forged by a massive direct collapse or inexplicable early hyperaccretion, the traditional model of a black hole growing slowly alongside a massive galaxy fails here. We now have two distinct physical pathways for hostless black holes: violent kinetic ejections in the modern, mature universe, and direct heavy seed collapse at the very dawn of time.
Both models stretch the boundaries of known theoretical astronomy. But observational astronomy is notoriously tricky. And some vocal critics argue that the absolute simplest explanation is being actively ignored. Are we being fooled by our own instruments? And could be
Before we permanently rewrite textbook astrophysics to accommodate naked supermassive black holes, we must carefully rule out the conventional cosmic illusions capable of hiding an entire galaxy. The most common culprit is interstellar dust. A massive, active black hole can easily outshine its surrounding stars, especially if those stars are buried behind thick columns of molecular gas and cosmic dust. Take the case of HE 0450-2958, the original naked quasar discovered in 2005. At first glance, through the optical sensors of the Hubble Space Telescope, it appeared completely isolated, floating alone in the void. The extreme luminosity of the active galactic nucleus created a blinding glare. Because astronomical telescopes have strict photometric contrast limits, it was entirely possible that a host galaxy was present, but simply mathematically impossible to resolve against the blinding center of the quasar. Follow-up observations using advanced radio and infrared telescopes eventually revealed a different picture. Data from arrays like ALMA, which can peer through dense material, detected a highly obscured, star-forming host galaxy right where the black hole was anchored.
The dense dust lanes had effectively acted as a cosmic cloak. They absorbed the visible starlight, blinding standard optical sensors and creating the illusion of a completely naked quasar. Beyond dust obscuration, another major illusion is simply a matter of geometry. When observing structures billions of light years away, a specific viewing angle can easily mimic the dynamic signature of a runaway black hole. In 2023, the Hubble Space Telescope discovered a 200,000 light-year streak of newborn stars trailing from a dwarf galaxy called RCP-28. Astronomers initially determined this linear feature was the glowing wake of a 20 million solar mass black hole, propelled at 3.5 million miles per hour through the intergalactic medium. However, researchers utilizing the ASTRID cosmological simulations proposed a compelling alternative. They demonstrated that this streak could alternatively be a thin, bulgeless galaxy viewed perfectly edge-on. If you observe a flat disk of stars from its exact edge, it creates a bright, sharp line. On a two-dimensional sensor, this geometric alignment looks almost identical to a high-speed ejection wake.
This debate forces observers to ask whether they're tracking the kinetic aftermath of a violent gravitational slingshot, or just looking at a normal, rotating stellar disk from a highly misleading, flattened angle. This is why confirming a truly hostless supermassive black hole requires immense epistemic rigor and multiple wavelengths of light. If high-resolution sub-millimeter arrays detect a rotating disk of cold molecular gas exactly at the site of the quasar, a hidden host galaxy is definitively confirmed. But even when we systematically apply these rigorous observational filters, some anomalies survive the test. While the nature of the RCP-28 wake remains heavily debated, the distinct kinetic separation observed in merging candidates like CID-42 remains a robust, verified example of a displaced black hole. filtering out the illusions of dust extinction and edge-on galaxies leaves us with a refined, highly vetted list of true wandering giants. But if these massive singularities are genuinely roaming
The idea that a singularity with the mass of millions of suns is roaming the intergalactic void naturally sounds like an apocalyptic threat. It is remarkably easy to imagine an invisible, unstoppable force wandering in the dark, devouring everything in its path. But astrophysics requires us to dispense with these sensationalist myths. Black holes do not function as cosmic vacuum cleaners. Their gravitational reach is strictly finite, and they only consume matter that directly crosses their innermost stable circular orbit. A hostless supermassive black hole did not devour an entire galaxy of stars to end up alone. Furthermore, the sheer scale of the universe makes an Earth encounter statistically impossible. Every confirmed runaway candidate resides billions of light years away from our solar system. Stripping away the science fiction illusions and the pop culture fears leaves a physical reality that is far more elegant. A true wandering supermassive black hole is not an invisible hazard. Instead, it is a highly luminous, gas-shrouded object safely confined to deep space. When a black hole is violently ejected from a galactic core by an asymmetrical gravitational wave blast, it does not leave empty-handed. The kinetic kick happens so rapidly that the black hole takes a vital piece of its old home with it. The physics governing this escape are defined by orbital mechanics and a critical threshold known as the bonding radius. This boundary dictates exactly what material the escaping black hole can successfully hold on to during an extreme kinetic ejection. During the gravitational slingshot, any dense gas within the inner accretion disk that is orbiting the central singularity faster than the galaxy's ejection velocity remains tightly gravitationally bound to the black hole. Gas residing outside that specific bonding radius is violently stripped away, left behind to slowly settle back into the merging host galaxy. But the tightly packed inner disk travels with the runaway black hole as a permanent glowing shroud. Because it carries this localized, high-density fuel supply, the ejected black hole does not immediately drop into darkness. It continues to actively feed on the trapped gas, burning brilliantly as a quasar or an active galactic nucleus.
According to current accretion disk kinematics, this retained gas reservoir is incredibly massive. Models show it provides enough continuous fuel to sustain a highly luminous active phase for over 10 million years after the black hole has fully escaped its host. This retained activity and immense speed make them spectacularly observable. In early 2026, the James Webb Space Telescope captured a definitive infrared bow shock ahead of a massive runaway black hole known as RBH1, proving these wanderers violently interact with their surroundings. Plowing through the diffuse circumgalactic medium at roughly 2.2 million miles per hour, the runaway black hole's sheer kinetic force compresses surrounding gas. This massive shockwave actually triggers rampant star formation, leaving a 200,000 light-year trail of newborn stars. We know these isolated giants exist, and the orbital mathematics dictating their retained accretion disks perfectly match our modern telescope data. The physics of gravitational recoil are now a confirmed, fundamental addition to galactic evolution.
But to prove definitively when and how these violent ejections happen in real time, we need a fundamentally new way to listen to the cosmos. What upcoming observation will finally catch the... To truly solve the mystery of the wandering black holes, we have to stop looking at the light they emit and start listening to the fabric of space itself. Right now, our best evidence for gravitational slingshots comes purely from the aftermath. We are limited to observing the glowing star-forming wakes, like the one trailing dwarf galaxy RCP-28, or the kinetically displaced quasars captured by telescopes like Hubble and Chandra. But these are just the lingering footprints of a much older cosmic violence. To catch the precise moment a supermassive black hole is violently ejected from its host galaxy, we need to observe the actual collision in real time. We need a completely different kind of scientific instrument that does not rely on light. This brings us to the planned LISA mission, the Laser Interferometer Space Antenna. Scheduled for launch in the mid-2030s, LISA represents a monumental shift in multi-messenger astronomy and how we will map the darkest corners of the universe. LISA will not use traditional mirrors or glass lenses to gather ancient starlight.
Instead, the observatory will consist of 3 separate spacecraft flying in an immense equilateral triangular formation trailing Earth's orbit around the Sun. By constantly firing precise lasers across millions of kilometers of empty space between the probes, LISA will be able to measure the minute stretching and squeezing of space-time itself, capturing the passing waves of gravity. When 2 supermassive black holes merge at the center of a colliding galaxy, they emit powerful, low-frequency gravitational waves. Current ground-based detectors, like LIGO, are only sensitive enough to hear the rapid chirps of stellar mass black holes. But LISA is specifically architected to detect the deep, slow ripples generated by the collision of supermassive giants. This capability is exactly what is required for the direct detection of a recoil kick in progress. By rigorously analyzing the exact shape and asymmetry of the gravitational waveform, astrophysicists will finally be able to calculate the precise mass ratios and spin states of the merging supermassive black holes before they become a single entity.
That specific mathematical signature will tell us the exact velocity of the resulting slingshot. It will definitively prove, without relying on visual interpretation, how often these mergers generate enough asymmetrical force to achieve galactic escape velocity. While we wait for LISA to open this new gravitational window, the James Webb Space Telescope is systematically hunting for early universe-heavy seeds. To do this, JWST utilizes advanced coronography, an instrument feature that physically blocks the glare of the central quasar. By artificially eclipsing that overpowering central light, astronomers can carefully search the surrounding dark space for ancient starlight. This is the crucial test to separate a truly naked, direct collapse singularity from a black hole that is merely outshining its starry host galaxy. The observational timeline is set. Between JWST peering deep into the cosmic dawn to find pristine heavy seeds, and LISA preparing to listen to the violent recoils of the modern universe, the classical model of the static galaxy is completely over.
Galaxies are not just serene, permanent containers for their central black holes. They are dynamic, violently shifting arenas. When LISA finally turns on its lasers, how many